Hello everyone, welcome back to our turbulence modeling videos. So in the last video we were talking about how we arrived at this equation here and how we're going to do subgrid scale kinetic energy modeling, at least the transport equation of such. Now I'm not going to fully derive everything because it's going to be quite a mess trying to sort through all these terms and doing the filtering. But at least I want to show you where this kinetic energy comes from, and what we do is that we multiply this equation, the unfiltered part, by the unfiltered velocity, so that we have a ui squared. Then after that we go term by term to try and get expressions of subgrid scale kinetic energy. So for example, the time dependent term here, it can be written as such. And if you want to combine this term, this ui prime term in here, you can consider the following derivative. So del by del t of ui prime squared equals to 2 ui prime del by del t. Okay, so del by del t of ui prime. So you just do some simple rearranging and you bring the half in. You will get this expression here. This thing here will be the kinetic energy. So this term here equals, this is where you'll probably get your kinetic energy term from. Okay, KSGS will be somewhere here. Okay, so this one will be the advection term. Again, it's another mess of terms. But using a similar process, we can try to bring ui prime inside. Okay, now you'll know that there are a lot of terms here, so I didn't fully derive everything, but you will be able to find some sort of rearrangement that will get you the KSGS. So for example, we'll do the same trick we did before. We'll try to separate these out term by term, and we'll try to bring the ui prime inside the derivative, and doing so we try to differentiate it such that one of the terms here will equal to this, alright, and the other term we'll try to deal with it later on. So what do I mean by that? When I differentiate this, I'm trying to bring this term out, so I'm going to bring this term and paste it here. Okay, and by product rule, these two terms will, the other term will be these two terms on the outside and the differential of ui prime here. Okay, right, so and then we try to deal with the other terms as well. For example, you have this term and this term. Okay, something special you will notice about them is that this ui bar plus this ui prime, when you add them together, because these two are the same, so if you notice, I'm taking this term and this term out, I'm putting it here. So you see uj bar, ui prime, uj prime. Okay, if I add them together, the uj bar and the uj prime will just give you uj. So if you were to do a similar trick, we can actually get the following expression, where ui prime, we just multiply ui prime to this term, and we will have this term over here. So doing so, yeah, we can try to get some form of subgrid scale kinetic energy. So what we have is this term. When we combine this term and this term, combine this term and this term, and what we get is over here, and we try and combine this term in here, so resulting in this term over here, this del by del xj, uj, ui prime. So one of the things is that we can try to bring ui prime out. Okay, we can bring the ui prime out, and del by del xj, ui prime uj. So this is this term here. Then this extra term I highlighted in yellow pops out, and what I want to do is to try and make this thing look like some subgrid scale kinetic energy. So I multiply by half throughout, resulting in this, and this is where my subgrid scale kinetic energy will come from. And since this is the term that I want to kind of substitute out, okay, I will have this term and I'll bring it to the other side. So since this is the term I want to substitute, I will have ui prime del by del xj, ui prime uj, that will equals to 2 times del by del xj of uj times this kinetic energy term, alright, times this kinetic energy term, and this extra term pops out. So to simplify this thing and then try to in some way bring out the subgrid scale kinetic energy, we can rearrange the terms over here as follows. We'll have this kinetic energy advection term here. Of course, you have two of it, and you have this term here and you have this term here. So there are lots of kind of leftover terms, but the idea is that you can find the subgrid scale kinetic energy advection term over here, and it comes from this advection term here. Of course, there'll be other residual terms that come about, okay, for pressure effects, okay, because there'll be this term. For pressure effects, we can kind of leave it be, and I'll show you why in a bit. For this, okay, this term, the diffusion term, it will get separated out into a few terms. Okay, you'll get separated out into a few terms. Okay. Now for diffusion terms. So I went through the first three terms rather quickly. It is this term here, which you can find the subgrid scale kinetic energy. This term here, which you will find the subgrid scale kinetic energy, plus a few other terms. Of course, you need some manipulation to do it properly. I just briefly go through so as to show you, yeah, where does this subgrid scale kinetic energy come from. This term I kind of leave it alone. This term you can almost get some subgrid scale kinetic energy there, because you have a ui prime here and a ui prime here. So we'll try to do something to that effect, and of course there'll be this other term here, and we'll need to deal with that as well. But I'll try to get us to the point, at least, to see where this subgrid scale kinetic energy comes from. So I'll just do the first term here first. Okay, and I have this, and what I want to do is to bring this ui term, okay, I'll ignore the viscosity. I want to bring this ui term into here. Okay, so what I can do is I do a second derivative. Of ui prime squared. Okay, what will happen is that we'll have a del by del xj on the outside, and this will happen. Okay, this will happen here. You have a second derivative. Alright, what will this term become? Okay, this term actually sort of becomes your kinetic energy term, right? Okay. This term sort of becomes your kinetic energy term. So it is 2 times the derivative of your kinetic energy term, half over here. So this should let you see where this kinetic energy term comes from. Now, of course, I will need to actually make this term look a bit more like this term. So I'll actually do the differentiation out. So let's do this. 2 times ui prime del by del xj of this. Okay, so what happens is that you will have a product, so to speak, 2 of this term, this whole term here, squared. Okay. Okay, so hold on. I need to do a proper product rule. So I'll bring the 2 on the outside, and I'll say I want to differentiate this and then multiply by this side. That's sure. Then I want to plus ui prime plus ui prime, and then we do a second derivative of this. Alright, so here we have the following. We have the term that we want, which is this term here. Yeah, we have this term here, which is this term I'm highlighting. Okay, this term I'm highlighting here, which is this first term. You actually will find it here because this is a second derivative after all. So I will just make it clearer over here. Okay, so making this a subject, okay, I will have this equals to the following. Yeah, I'll have this equals to the above here. So I obviously can take up the 2 on both sides, and I will have this thing become the subject, and I will have a negative of this plus this term. This is a second so-called this is a second derivative of the subgrid scale kinetic energy. All right, so this is where our K comes from. This is where our K comes from. Of course, there'll be filtering and all that, but you'll see that this term actually gives rise to this term here. All right, so let's do just that. All right, we have this term, which will be this term, and then now we want to deal with the other term, this one and this term. So let's deal with the other term. Okay, so del ui del by del xj of this. Okay, so we try and do the same thing. Can try and do the same thing. And first thing, I mean, to make things easy on ourselves, we can try to swap these 2 derivatives around. So this one, because it's a divergence anyhow, this is actually divergence of some vector, so it becomes a scalar very quickly, you'll see. Okay, swap these 2 around, because it doesn't really matter which order you differentiate it. And then of course that makes things a lot easier. You can actually just change the index, because there's only one index here, by the way. You know what, I think, yeah, you better don't mess around the indices first. Okay, anyway, so we'll try to do a similar trick, all right, to what we have here. In fact, if you take a look, the way that so let's try and do it properly and see what terms come out. So we'll have del by del xj partial by partial xi u I prime u j prime. Okay. Okay, so anyway, yes, I fast forwarded this product rule. This is what we get, and Yeah, from the way this looks, it looks as if we're going to get some form of second derivative here. It looks like we're gonna have some form of second derivative, and this actually looks as if it's like one of those Reynolds stress components. So actually I don't think we need to deal with this, but what the important thing I want you to see is that from this term here we can get the kinetic energy term as well as this term. This term is actually written like so. Okay, del ui prime del xj. Okay, so it's squared plus this kinetic energy looking like term. Okay, so this is the viscosity term. Okay, the viscosity term here. This one we kind of just leave it be because we'll model this anyway. But all in all, when we put this down, all right, when we put this down, it may not be so accurate, right? I'm just giving you a rough idea. Okay, replace terms with K terms. Yeah, I'm gonna replace the terms with the subgrid scale kinetic energy terms. I mean, I haven't filtered and everything, but just want to give you a rough idea where these things come from. For example, the time term here, it goes directly here. We just showed you that. Just now. Plus, all right, we have this advection term. The advection term is these over here. Okay, we'll have some advection of kinetic energy. All right, we'll have some advection of kinetic energy. Of course, there's a factor of 2 there, of course, and we can do away with it by substituting this. We can substitute this in so that we get one time less of this kinetic energy term. So let me just do that. Again, the idea is that I'm not going to do the derivation to full, but just want to show you where this KSGS might come from. Okay, so this is the KSGS term. These are all the other terms that pop out. Okay, then we have the other bottom where we have the pressure term. I will just leave the pressure term be, and we'll have this, which it becomes these two terms. All right, one is this term I was talking about, the viscous diffusion term. And then the other term is this term here. All right, this term here, and this term here, I can just pretty much say is the subgrid scale kinetic energy. So we have a second derivative of that. We have some funny dissipative term here. Okay, and then we have the stress tensor term, the subgrid stress tensor term. Okay, so that's what we have. All right, we can take a look at this equation. We are sort of almost there. We have this time derivative term. We have an advection term, but we have these two terms that we don't really know what they are. All right, these two terms. So to find out what these two terms are, we can take a look at some of the constitutive closure relations. Okay, some important closure relations for the terms. Okay, so you have one thing is that, okay, we have the pressure term here. Okay, so after you do all this, you're supposed to filter. But I kind of just skipped that step just to roughly show you the concept of where all these terms come from. One term is this filtered, this half ui uj term. Then you filter all of it. So product rule, we can do this expansion thing, but it will probably come out to a lot of partial by partial xj terms, and you have ui prime uj, blah 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 blah, etc etc. Okay, I'm not going to do those terms, but I just roughly show you probably which terms these are referring to. These are referring probably to these 3 terms here, or these 4 terms here, which I want to give you a green highlight. So this is the green highlight term. Okay, so these are closure relations. This one probably comes from the pressure term, so I'll give you a yellow highlight. Yellow highlight will be this term here. Okay, so this pressure term will probably come from that. Yeah, and then these 2 terms, this term is actually what comes about. All right, and where does the turbulent viscosity come from? If you take a look at this term here, you see a turbulent or subgrid scale eddy viscosity. Nu t is actually equals to this term. You see this term? This term actually you have some filter width and some KSGS, right? So the filter width is this one here. All right, the filter width is this one here, and you have the KSGS square rooted. Okay, so this is where your mu t comes from, and this term here would correspond to this term over here. Okay, it will correspond to this term over here. So this is the green and yellow term, so to speak. Now then you have this other closure relation over here. Okay, you have this other closure relation, so to speak. Okay, I hope I didn't mess up too many of the correlations. Okay, but I may have been off by a factor of 2 or what not have you. But you see this term here, I will put it as maybe a cyan. Okay, this is the dissipative term, and it's equals to C1 KSGS over delta, which is the filter width, and this corresponds to this term over here, the CE KSGS to the 3/2 over delta. So this is the cyan term, and the cyan term will probably come from here. Okay, because that's the del ui del xj, this term over here. So this is probably where the closure relation for this comes from, and you have a bunch of remaining terms for viscosity, and of course you have this one, but I think mentioned before, if you have a second derivative of k, like you do here, the second derivative of k, usually we can neglect this neglect in turbulent zone. Okay, nu SGS equals to nu t. All right, I use that notation. It's much more than nu. So this term you can kind of neglect. So I will just put it in gray. Okay, so this term we kind of neglect because it's combined into this turbulent viscosity term here. So since the turbulent viscosity is much greater than the normal viscosity, we can kind of just do away with it or neglect it. And then you have this tau ij term, which will correspond to this. Of course, this tau ij is actually outside. So probably there's probably some math magic there. Okay, lots of derivation steps which I skipped, and this other term, probably fit it, somewhere between the diffusion and dissipation term. Okay, so yeah, I gave you a very rough outline of where each term comes from, which term corresponds to what, at least on a very high level, conceptual level. I didn't do a thorough mathematical, balanced term by term, but at least show you where each term comes from. So this is a time derivative term. This one is the advection term. Ooh, lightning. Yes, advection term, and then this one is the this one's probably subgrid dissipation. That means the kinetic energy the turbulent kinetic energy has to dissipate somehow into heat or what have you. And this one also is a dissipation term. Okay, viscous dissipation or subgrid dissipation. Okay, so there are two mechanisms at play probably, the viscosity as well as the subgrid viscosity. The both of them contribute to this dissipation of kinetic energy. Okay, so and then we have this term which is probably a diffusion term. It's a diffusion of turbulent kinetic energy. Alright, so kinetic energy can like diffuse across the space. This term will probably deal with that. So that's a very rough overview of the K-equation. Okay, so K-equation is just here to keep track of this subgrid scale kinetic energy and to make sure that you don't have an indefinite backscatter without, and then you have a very non-physical result. Okay, dynamic K-equation is probably just K-equation. I mean, the main thing is that CD here, okay, CD in this formula, CD here in this formula is not constant as in the Yoshizawa model. Probably you have a Kim and Menon model. But the idea is that CD is not constant, and we probably get CD using some sort of double filtering that we talked about in this the dynamic equation before. So this is just a rough introduction. I'm not going to go in detail, but this is roughly what the K-equation is. So it is as it is, it's a probably very good very good for keeping track of this subgrid scale kinetic energy, and it can deal with the backscatter problem well. And the solver, this algorithm or this system of equations is pretty stable, so it can help to deal with the dynamic bit. And that's where we have those equations from. Okay, so that's it for K-equation. I'm just covering it very briefly. The next video we'll probably look at some other models. Thanks for watching.